Hello and welcome back to Calculus 3, the last section of chapter 15 on Lagrange multipliers. This is very useful section. It's applied. We can calculate min and max values of a given function shape or implicit shape with a constraint, which means there has to be another equation that will provide the constraint, and then we'll find min and max with that constraint in mind. You have seen this in the example yesterday when I did that word problem with the farmer, and I said objective equation was to create the maximum area. The constraint was that you have to use 2,000 yards of fence to make everything work, right? So that was our constraint, 2,000 yard of fence. So today we're going to have the same deal, practically. Now, the process, there is no definition or a theorem or anything. It's just a process of how you solve these problems. It's just word problems for min and max. So the process. Number one, get objective f and constraint g equations. I'll say, look at that now. Just get those. 2 use del f equals lambda del g to get system of equations. Number 3, solve the system to find, let's go solve the system so solve the system to do what? Solve the system to obtain min max of f along G. So that's the procedure. You read, if you have a basic problem, then you just start with number 2, and if you have a word problem, then you will have to translate words into equations, and then from there go and do number 2 and number 3. We will start with vanilla problem, and this can be done with a 2D or 3D input. It's because, again, guys, this is a vector equation, so if you have a 7-dimensional input, you will just, have 8 equations, and yeah. So here we go. We'll do the vanilla problem first. Let's say number 8. F of xy is given as xy squared, and subject to x squared plus y squared equals 1. Okay, so I have my f, which is xy squared, and I have g, which is x squared plus y squared minus 1 equal to 0. So we write both of these functions this way, and now we find del f, which is the vector of partial derivatives. We did that 2 days ago. We know it's a vector of partial derivatives of f. So fx is y squared, and fy is 2xy. Now I need to find del g, which is gx, gy partial derivatives. So that's just going to be 2x and 2y. So we have equations given. We find both of these gradients, and then we use the formula del f equals lambda del g, which means that the vector y squared 2xy is equal to the lambda times vector 2x 2y. So you plug these two vectors into the equation. This will provide you with, in this case, two equations when you set the first components equal and the second components equal. So y squared is equal to lambda times 2x. That's the first equation. And the 2xy is equal to lambda times 2y, which is the second equation. Now, as you can see, you have three variables and two equations. You need another equation. We always use g as that last equation that you will always need. When we do the three-dimension case later, you will have equation for the first component, equation for the second, equation for the third component, but then there will still be x, y, and z, and there will still be lambda. So again, four variables, you will need to use equation g again. So equation g is x squared plus y squared equals to 1. So this over here is your system. We do not care about lambda. I know, sad and cruel. We only want x and y because those will give us points at which we get to see min and max. So you are going to somehow solve this nonlinear system. It's a nonlinear system because you have x times y, you have x squared, you have y squared. These are not linear systems, and there are no rules on how to solve these systems. So whatever works, do it. If you have to crank open a new bottle of essential oils, by all means. I heard they do wonders. I don't know. So my approach to the nonlinear equations is usually to kill lambda immediately, if it's possible. For some systems, you will have to compute the value for lambda first, even though you don't care about it, and then use it to solve the rest. And in most of the other cases, you will be able to kill off lambda before you do anything else. Now, the other part also, which is a pitfall here, is values x and y could be 0. And if they are 0, you are not allowed to divide by them. So if you are, it's much better and much easier to work on word problems where you know that x and y are either distances or something that you know it's not a 0. And in that case, solving equations is much less of a problem, because you know that you can divide both sides by x, you can multiply, you can divide both sides by y, and so on, when you know that they are not allowed to be zeros. Remember, if I am working on a problem for the farmer, and the farmer has 2,000 yard of fence, and I'm looking for x by y dimensions, Well, neither of the two can be 0, because in order to have a rectangle, this has to have some length and this has to have some length. If either one of the two is 0, then I don't have a rectangle, right? If you say y is equal to 0, then I just have line x like this. And that's nothing, right? So, solving the system, it's either going to be 3 equations, like in this case, or it's going to be 4 equations when we do the 3D case. Now, the way I'm going to do this is, from the first, I'm going to solve for 2 lambda. So 2 lambda times x is equal to y squared. And on the bottom, 2 lambda times y is equal to 2xy. And then I have x squared plus y squared is equal to 1. So clearly, those x and y with lambdas, they need to be divided so we can get rid of them. But remember, we are not supposed to do that. So you have to, in this case, if there is no way around it, you have to check if zeros are possible solutions. So if x is a non-zero number, we are all good to go and divide by x. If y is a non-zero number, we're all good to divide by y. So if I write 2 lambda is equal to y squared over x, that just means that x cannot be 0. That's all it means. And if I write 2 lambda is equal to 2xy divided by y, from there I am stating that y cannot be 0. And those are, right, now big claims. Because I don't know, this is not applied problem, so they could be 0. So we have to take that. Now, both of them at the same time, if they are 0, then it's not going to work in here. So solution 0, 0 is definitely not a solution. But 1, 0 could be a solution, or 0, 1 could be a solution. Right? So when you have to make these cases somehow work in your head, and that's a lot of practice with this nonlinear systems. So in order, right, if x is equal to 0, then y must be 1, and if y is equal to 0, then x must be 1. So would any one of those work in any of the other equations? And the answer is no, right? So there is a lot of subtleties to consider when you're solving the systems. All right, so which one do I get to keep? Well, I would like to keep the bottom equation because it isolates 2 lambda and it kills y at the same time. But we have to bring baggage with it that y is not allowed to be 0. And then we have to try and solve the rest of the system trying to force y is equal to 0. So I'm going to keep the bottom one, not the top one. And just remember to check for 0 if you force it. Say y is equal to 0. So we'll use this. Now let's see. If y is equal to 0, that implies that x is equal to 1, and you get the point 1, 0. So now, if you plug in 1, 0 in a problem, you will figure out if it's possible to solve it at all. So if y is equal to 0, then x must be 1 because of the third equation. So now I plug in these, I get 2 lambda is equal to 0, from where calculate that lambda is 0. So now when I plug that in here, I get lambda is 0, y is 0, equals to 0 is equal 0. So wow, this actually works. 1, 0 is one of the solutions. Okay, So we'll keep that one because 1, 0 works in all equations. Because if lambda works out to be 0, let me just check one thing. Okay, so we have that 1 point now. So the rest is now solve the system. So this was like a little aside, because we said y cannot be 0, so that we can do the rest of the calculation. But then, because you don't know, you have to check if y is 0, and it worked out. So now I have this 2 lambda times x is equal to, so this is 2 lambda is equal to 2x. So now, instead of 2 lambda, so equation 1, instead of 2 lambda I get to write 2x, and then I still have times x is equal to y squared. We plug the second equation into the first. Plug in. And then we still have x squared plus y squared is equal to 1. So now this gives us on the top 2x squared equals to y squared, and we still have x squared plus y squared equals to 1. So now we can use the substitution rule, and we have x squared plus 2x squared equals to 1 when I plug top equation into the bottom, replacing y squared. And I get 3x squared is equal to 1. X squared equals 1/3, from where x is equal to plus minus root 3 over 3 when you rationalize. So I have my x's, and I can now solve and get y's. Now, the 2x squared is equal to y squared is a fast equation to deal with it. We know that x squared is 1/3, so 2 times 1/3 is equal to y squared, from where y squared is equal to 2/3. And now when you take the square root of both sides, y is equal to plus minus, that's a root 2, root 6 over 3. So there they are. We have 4 points on the pile right here, and then additional point 1, 0, which we calculated earlier. So we have root 3 over 3, root 6 over 3, root 3 over 3, negative root 6 over 3, negative root 3 over 3 and root 6 over 3, and negative root 3 over 3 and negative root 6 over 3. And 1, 0. So we have 5 points that we were able to find that will give us these values. Want to take a look at another example? And I would like to find a word problem, and then we're going to take a look at the 3D. So this is the 2D case, right? 2D domain. So I'm looking for a word. Problem with beautiful. Maximum perimeter rectangle in an ellipse. So you have, this is problem 31. You have an ellipse, and then you are going to inscribe a rectangle in that ellipse. So when you have this situation, ellipse is given as 2x squared plus 4y squared is equal to 3. So that's your ellipse. Now we are not used to equation of ellipse given this way because it's supposed to be equal to 1, so you should divide everywhere by 3 and figure out what the radius is, but actually we don't care about it, it's just what we do here. So they want the maximum perimeter find the dimensions of the rectangle. So find the dimensions of the rectangle. So this whole length over here is A, and this whole length over here is B. So find A and B. With max perimeter. Great. To achieve that, we're going to take a look at a point here. Just call it xy. That's a point. Now, this length is x, this length is x, this length is y, this length is y. So our A is clearly 2x, and our y is 2b, and our b is 2y. Our b is 2y when you look at the picture. So I'm trying to maximize perimeter of the rectangle. So what I need is 2a plus 2b to be max. And that's your objective equation. Now you have that a is 2x, so that's 4x plus 4b needs to be max. The constraint is that the rectangle is stuck inside the ellipse, and ellipse has the equation, so that has to be your constraint equation. Your objective equation is the only one that you are looking to maximize or minimize. So, f of xy is given as, oh, this is supposed to be a y over here. 4x plus 4y. So this is my objective equation, because I want to maximize the perimeter. And then I have g of xy, which is equation of the ellipse, 2x squared plus 4y squared minus 3 equal to 0, constraint. So I have my two equations. Remember, this was given to us, previous problem. Now we actually had to think a little bit and come up with these. So this one is the perimeter, right? The F is the perimeter, and trying to maximize that. So that's going to be objective equation. And the whole rectangle has to fit within the ellipse, which is why ellipse is a constraint. If I change the constraint, the problem changes. So I have this, and we just go del F equals lambda del G. So del F is 4 equals to lambda. Del G is 4x and 8y. You can find these gradients on the side if you want, and then put everything in a formula, or you can just directly go into the formula. So now, once you have this, you go and create equations. So 4 equals 4 lambda x, 4 equals 8 lambda y, and the constraint equation, which is our ellipse equation. We'll go all the way up there and just copy it in. There we go. And now I have my 3 equations, which is a system. Now these equations are great because first of all, we know for a fact that x and y are not allowed to be zeros because those are lengths of the rectangle, and if either one of those is 0, the whole problem doesn't exist. So, since x and y are lengths, x cannot be 0, y cannot be 0, so we can divide whatever we want, right, by x and y, which is great. So let's simplify the system. Divide both sides by 4. I have lambda x equals 1. Divide on the second one, everything, you get 2 lambda y equals to 1. And the last equation stays as 2x squared plus 4y squared equals to 3. If you can, kill lambda right away. So from the first equation, lambda is equal to 1 over x. We are allowed to divide by x because x cannot be 0. X is definitely not 0. Plug into second equation. 2 times, instead of lambda, I have 1 over x, and then times y equals to 1. So we have 2y over x equals to 1. From where we can just write 2y equals x when you multiply x to the other side. So now we will plug this one into the third equation, replacing the x with 2y. So 2 times 2y squared plus 4y squared is equal to 3. Two squared is 4 times 2 is 8. Y squared plus 4y squared is equal to 3. There will be 12 y squared equal to 3, from where y squared is equal to 1/4. And finally, y is equal to plus minus 1/2. Write this in blood next to it. Square root both sides, plus put plus minus, right? You know how many times you forget this? It kills either half or more than half of your solutions. So if you square root both sides, you have to put plus minus on one of them. So we have plus minus 1/2 on the y. So x is equal to 2y. X is equal to plus minus 1, because y is 1/2. 2 times 1/2 is 1. So plus minus 1. This gives us 4 points, which makes perfect sense, because when I drew the picture, do I have 4 corners? I do have 4 corners, right? You see them? You see all 4 corners. So all 4 corners are given by these numbers. So the vertices of the rectangle are 1 and 1/2, 1 and -1/2, -1 and 1/2, and -1, -1/2. So these are the vertices of the rectangle. And you can see that the rectangle is now 2 by 1, right? Because it goes from -1 to 1, that's 2 units, and from -1/2 to +1/2, which is 1 unit. So so we can calculate now what is that maximum perimeter. When you draw this, you will go let's go. So -1, +1, +1/2, -1/2. So I used, in this case, 2 squares as a half, 4 squares as 1, and then I can draw in the rectangle. I can draw the rectangle now, and if you take a look at its perimeter, right, you have a perimeter of 6. Because you use the corner points to create your rectangle, and then just calculate the perimeter. So you have 2 units on top, 2 units on the bottom, 2 + 2 is 4, 1 unit on each side, 1 + 1 is 2, 4 + 2 is 6. So the maximum perimeter, given the constraint that the rectangle has to be inscribed inside that ellipse, it gives us the perimeter of 6. So those are the 2 examples for 2D. Now let's go and take a look at x, y, z input. So now we're going to have linear systems that have 4 equations, right? Because we have x, y, z, and lambda. So we'll have 4 variables, therefore we need 4 equations. Let's do the vanilla case first when everything is given, and then look again at the word problem afterwards. So problems 17 through 26 are the ones that contain these. Now I would like to introduce something really cool. So I have to pick a problem carefully, and see something that I won't regret too much, but I still regret. 22. F of x, y, z is given as x plus y plus z. And you go, ho, 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 1, 1, 1, easy. Hold on. G of x, y, z is x squared plus y squared plus z squared minus 2x minus 2y minus 1 equal to 0. Good. So here are our 2 equations. Now we know the procedure. So we immediately come up with del f equal lambda del g. So 1, 1, 1 for f, and then lambda times 2x minus 2, 2y minus 2, and 2z. So these are my gradients, which are partial derivatives of these functions. Yes? That's this equation. when you take partial derivatives of each one of these. Del f, so I'm going to color code real quick. So del f is this, and del g, which are partial derivatives, del g, and then lambda is lambda. Partial derivative of g in respect to x is 2x, and then minus 2. The other terms don't have x in them, so those are all zeros. And when I take derivative, partial derivative in respect to x, is 2x minus 2. Awesome. So now we are going to take the first one, create first equation. So we have that 1 is equal to, you can kick 2 out, so 2 lambda x minus 1. Then the next one, I was purposely picking a problem like this for you'll see why now, y minus 1. And finally the third equation over here is 1 equals to 2z, and we have to use constraint g, which is x squared plus y squared plus z squared minus 2x minus 2y equal to 1. So there's my system. I'm sorry? It doesn't matter which form you use. I moved one to the other side, or, you know. It's usually given this way, but if you have it in the problem given and it's like, let's say it's equal to xy term, right? Then that term would also participate in the partial derivatives. So when we are talking about the constraint as a g equation, we want it equal to 0, but then it's more writing to have it equal to 0 when it's the part of the system, right? So it doesn't matter, right? It doesn't matter. Yes?
For the 1 equals 2z, is there something lambda there?
Oh, yes. Thank you. Yes, absolutely. 2 lambda z. Excellent. Yes. Good catch. I was testing you all, and obviously you're paying attention, so that's great. The rest of you, terrible. So I gotta solve this. I have to get x, y, z points out of this system. Now, I picked this problem specifically because something very useful is happening in this problem. Look at the first two equations. They are the same. If you are able to find a pair or even a three-way of equations where swapping x's with y's with z's is not making any difference, those values have to be the same in the answer. And that is reducing your calculations immensely. So I'll write this in blood over here because it's that important. These are called symmetric equations, and they immediately mean x equals y. That kills your variable right away. So symmetric equations. You recognize symmetric equations if you replace every x with y and every y with x, you still have same equation. Let's say you have x squared plus y squared minus xy. This is symmetric. If you replace x with y and y with x, you get the same equation. You get y squared plus x squared minus yx. Well, these things are commutative, so, right, it's symmetric. If I want to kill the symmetry, all I need to do is to change this into a minus. It's no longer symmetric, because now y squared minus x squared is not the same as x squared minus y squared, right? So symmetry is something that you exploit if you have it. And because these two are symmetric, you replace x and y, you get the same equations back. That immediately means that x is equal to y. Guys, if z joined in as well, like that, then it would be x equals y equals z, and you are talking about a cube, right? We don't have that case, but there is another problem that actually has it. If you look at the homework exercises between 17 and 26, you're going to find that one of those problems has a three-way symmetry, and about 4 or 5 have a two-way symmetry, which is great. So this immediately kills a variable, which is amazing. So now you can just eliminate, let's say, all y's, and you rewrite your system replacing every y with x. So the first equation survives, 2 lambda x minus y, x minus 1. The second equation, you're replacing y with x, and it's going to be the first, same as first equation, so we don't have to write it. 1 equals 2 lambda z. And then finally we have x squared, well, 2x squared, because y squared becomes x squared, plus z squared minus 4x equals to 1, because the y becomes x, and then minus 2x minus another 2x is minus 4x. Please note that every time, this is a good practice, guys, like an advice. Every time when I am dealing with equations, I always keep all of the equations, I keep rewriting even those that I never used, because I want to have them all together and see. If you are working fractured, right, you write a little bit here, write a little bit here, write a little bit there, it's just very hard to follow where the stuff is. So the first set of 4 equations is in its own box, and I did something with it. And then now I have, this is like a completely new problem. I can disregard everything that happened previously, because I have all 3 equations with all 3 variables in front. I don't have to scroll up, I don't have to look up anything. This is like a new problem. This is me assigning a problem in my pre-calculus 1 class, and I say solve this system in chapter 7, right? They don't have to know any of this stuff up there, because you have 3 standalone equations. Great. The next step for us is to eliminate lambda, because we don't really want it around. And remember what I have to do now? I have to say that lambda, well, 2 lambda, it's better to use 2 lambda because I can replace 2 lambda as a unit. So 2 lambda is equal to 1 over z. I divided by z, which means that z is not allowed to be 0. But z could be 0? So let's check if it's possible to solve the problem if z is 0. If z is 0, then you have equation 1 equal to 0 from here. Do you see that? And that's no bueno. So z cannot be 0 because this equation cannot hold. So we don't have to do any extra work. Dividing by 0 is okay because z cannot be 0. Awesome. Now we plug in. Remember what I do. I write 1 equals, instead of 2 lambda, I have 1 over z. And then I have x minus 1. And I am still copying the second equation. I haven't touched it. But again, I put them together, and look, it becomes a completely new problem, independent from everything before. I have z equals x minus 1, and I still have 2x squared plus z squared minus 4x equals 1. Again, two equations completely independent of what happened before. This could be a start of a new problem. Plug in. Two x squared plus x minus 1 squared minus 4x equals 1. And guys, this is the same as problem that you would have on your algebra 1 to solve a quadratic equation. 2x squared plus x squared minus 2x plus 1. When you expand, don't forget the middle term, your Calc 3, equals to 1. Fix this as much as possible. You get your 3x squared minus 6x, and 1 cancel. Oh, this is so good because it's equal to 0. You factor out 3x, you are left with x minus 2 equals 0. And now by the zero product rule, 3x equals 0 from where x is 0, or x minus 2 is 0 from where x is 2. Well, that's great, because having x equals 0, x equals 2, you immediately know that y coordinate has to be the same, so you have x equals y, that was given before, so you know immediately that y is equal to 0 and y is equal to 2, which creates so far 0, 0, comma, question mark, and 2, 2, comma, question mark. That's where you are currently in this state of affairs, right? And now all you need to do is to go and compute the z value using either constraint, or if there is anything that is more convenient than that. Now, we did have an equation which links nicely z with x, so z is just 1 less than x, which is great. So z equals x minus 1. So in this case, z equals negative 1 and z equals 1. So I have my 2 points, 0, 0, negative 1, and 2, 2, 1. So these are my points, and the problem is solved. These systems become a living nightmare when you don't have symmetry, because you don't get to kill any of the variables instantly, and you have to go and keep trying one way, another way, and keep checking. If you divide by x, can x be 0? So you have to do that case as a separate problem on the side. These systems can be really nasty and can produce very lengthy and painful calculations. We haven't seen any yet. All of these was smooth sailing in terms of solving systems. I mean, considered smooth sailing in solving systems. So your savior, symmetric equations, when you can replace x, y, or z with each other and not change the system, it turns out to be a very nice calculation. So if I quickly show the homework blob, 17 through 26. Yes? 17 through 26. Look at 17. Subject to x squared plus y squared plus z squared. That is going to give you on G symmetry, but it's ruined by by x plus 3y minus z. That problem is not going to be symmetric. So solving this is going to be pain. The problem 18 gives you the symmetry x, y, z, but it ruins the symmetry with x squared plus 2y plus 4z squared. So no symmetry there either. It's a terrible problem. Symmetry is also ruined over here, but it's okay because it's just an x over there, so that's not a big deal. Problem 21, you have symmetry in x and y. Problem 22, you have symmetry in x and y. This is the one we just did. Problem 23, no symmetry, because you should have x, y, but then you don't have, if you had the 2y in here, then it would be symmetric. So x equals y would be easier, right? This one was so close, but no, because look, y and z should be symmetric, but they're not symmetric here. So I hope you see what the symmetry would look like. It looks like that if the two are symmetric here, the same two must be symmetric on the other side. Otherwise, you are doomed. So you have x plus y, and then x squared, and these two. You can't just have minus 2x and not have minus 2y. That will obviously throw symmetry off. So symmetry is not something that it's not something that it's really always there. It's rare. But when it happens, it reduces your calculations significantly because you are able to claim that those two variables are immediately the same, and that's reducing calculations a lot. So here are the word problems. We did maximum perimeter in a rectangle and ellipse. You also have maximum area of the rectangle or ellipse. You maybe want to practice that one for homework. Those are the two-dimension ones, right? Extreme distance to ellipse also, but you have to use technology for some reason, whatever. Here we go. Box with the minimum surface area. Very important to minimize the box that you will. Why? Why would you be hired by a company as a packaging engineer to design a box with minimum surface area?
For small box, makes less supplies used.
Yes. So if you are able to design a box that is going to shave off, 5 cents per production of a box, it's great. Why?
Because you're mass producing it. Because you're mass producing it, so it's 5 cents.
Exactly. It's 5 cents times 100,000 boxes. Maybe you have 1 million boxes. What's 5 cents times 1 million? Right? It's a lot. So it's a big saving. Right? When you are dealing with your own stuff, generally you don't care, right? 5 cents. Usually you don't even spend to pick it up if you find it. But when you are in a company and you are going to ship 1 million of something, 5 cents per box, right? That's a big chunk of money. So you want to save every cent of a cost. So sure, you are going to be hired as a packaging engineer to figure out the box of maximum volume and minimum surface area at the same time. Maximum volume means you can put a lot of stuff inside, and minimum surface area means the smallest possible box that will contain that surface area, that volume. Minimum surface area means the least amount of material used, and that's where you save the money because you use less cardboard or whatever your box is made out of. So we have a maximum. There are shipping regulations. Shipping company requires that the sum of the length plus girth of the rectangular box do not exceed 108. Maybe that would be a cool problem to take a look at. let's talk about shipping regulations. If you were dealing with the three-dimensional problems in your Calculus 1, they always made sure that they give you a square box with a square base. Because box with a square base will have x and x, and then you will just have y, and that's great. Two-dimensional problem for Calc 1. Now, that requirement doesn't have to be there anymore, because you have x, y, and z, three different lengths. And we have Lagrange multiplier that can be done over x, y, and z. So now we don't have to have that constraint that the base must be square. So problem 27 says that shipping regulations requires that the length plus the girth of the rectangular box does not exceed 108. So the longest it can be is 108. So let's draw a box, and this box is going to have length. Looks like a coffin, but whatever. So this is your length L. What is girth? The girth is going to go around the face over here. So it's the perimeter of the face plus the length. So my variables are x, y for the face, and another x and a y, and L. So immediately I have my constraint, because when you read the problem, the constraint is to be all of this to add to 108, right? So the constraint function would be 2x plus 2y plus L to be equal to 108 or less, but you want to maximize, so put 108. So we have that. And they want the max volume. So that's going to be our objective. Our objective is to maximize the volume under constraint that all of these red distances add to 108. Great. So who can tell me what is the volume of this box? Just crickets on the other end. Come on, guys. What is the volume? XYL. Thank you. XYL. So I have my, and that's a max. So I have my XYL. Perfect. If you're annoyed with L, you can change it into a Z, but variable is a variable. And my constraint function G is 2x plus 2y plus L minus 108 equals 0. And then later on, we're going to put it equal to 108 just so you're annoyed. Okay. The first thing I do, because I do this for a long time, is I look at these equations before I start doing Lagrange, just to see if I'm going to have a good time or a bad time solving them, right? And I can immediately see the symmetry in x and a y, so I know that the face is going to be a square. See, I have x times y. If I flip-flop them, I'll get yx. That's great. And I have 2x plus 2y. So unfortunately, this is not a 2L. If this was a 2L, then I would have a three-way symmetry. And a three-way symmetry would make everything to be a cube, x, y, z, right? It will be a cube. I mean, x, y, L. But I don't have a 2L, which means it's not a three-way symmetry. It's just a two-way symmetry because these are the same. Okay, great. Let's go do the Lagrange. So del F equals lambda del G. Now I need my three partial derivatives of F. partial derivative in respect to x is yl, partial derivative in respect to y is xl, and partial derivative in respect to L is xy, times lambda times the vector of partial derivatives for constraint G, and that's just 2, 2, 1. Oh, nice. I get to write my three equations now. YL is equal to 2 lambda, XL is equal to 2 lambda, XY is equal to 1, and I don't like this. I don't like this. Oh, it's equal to lambda, thank you. 1 lambda. And then we have the last equation, which is 2x plus 2y plus L equals to 108. There we go. So this is my system. And I am happy because there is a symmetry here. And that spells that x is equal to y, because, just take a look. We know that x or y or L cannot be 0 because these are all lengths of a package. Like, imagine if any one of the lengths in this classroom was 0. There would be no classroom. I don't care which one. Just one of them is 0, there's no classroom. You have to have a non-zero number in order to have a length. So if you consider the first two equations and substitute 2 lambda equals 2 lambda, you get YL equals XL. L, divide both sides by L, because L can't be 0, and you get x equals y. So now that greatly reduces our equations. So let's kill y everywhere. So I have my XL equals 2 lambda. I have my x squared equals lambda. We're killing y's. I have 4x, because 2y is 2x now. So 4x plus L equals 108. So when I plug in x equals to y in each one of the equations, I get a new system here. So now we have lambda is x squared, plug that in. We have XL is equal to 2 times x squared. And we still have 4x plus L is 108. So you can solve this any way you want. We'll solve for L over here, which is 108 minus 4x, and we'll plug that up there. So now it's x times 108 minus 4x is equal to 2x squared. That's 108x minus 4x squared is equal to 2x squared. 6x squared is equal to 108x. And we can divide by x because x is not allowed to be 0. So we have that x is equal to 108 divided by 6. 108 divided by 6. Now 1 plus 8 is 9, so it's divisible by 3, and it's even, it's divisible by 2, so this is evenly divisible. 6 into 10 goes once, 6 into 48 goes 8 times, so it's 18. Now, we know that x equals y equals 18. I believe these are done in inches. Yes, inches. And now to calculate L, we have 108 minus 4 times 18. L is equal to 108 minus, this is 40 plus 32, 72. So 36. So the dimensions of the box are 18 by 18, that's the face, times by 36 inches. Those are the dimensions of the box that will give max area, max volume, which you can compute in inches cubed. It gives you maximum volume, and at the same time has the constraint that the length will add to 108. So you have 18 times 4, because it's the perimeter of the face. So if one side is 18 and another is 18, then you still have 18 and 18. So 4 times 18 plus 36, it better be 108. And that guarantees maximum volume and length. So that's the Lagrange multipliers. In some cases, as I say, when you start working on the homework, you guys are going to run into these crazy systems that are not easy to solve. Make a note of them and bring them to class if you're not able to figure them out. So I'll struggle along with you. The important thing to understand is that if you're not working on a word problem, you cannot just divide by x or divide by y. It's not allowed. If you have to do it, then you have to make sure that the side problem is done as well. And that is forcing the variable to be 0 just to see if the solution is possible. I have done that every time today, but you know, it's a way to lose solutions. And I'm just going to illustrate that before you guys leave. You see, if you have an equation that says x squared equals 3x, it's not related to anything that you guys, there's no word problem to it, it's just an equation that is dropped at you. And you want to solve this equation. Well, some people will just say, just cancel x equals to 3 and you're done. Because 3 squared is 9, 3 times 3 is 9, 9 equals 9, we're good to go. Yeah, but that's only half of your solutions, which means you lose half of the points for the problem, if this is Algebra 1 problem. Your job is to solve it properly by subtracting 3x, factoring out x, and using zero product rule. And the second solution emerges immediately. So you see that? That's the one solution that you lost because you divided both sides by x, not knowing in advance that x, right, is or is not allowed to be 0. Now, this skill translates into other areas as well. What if you had sine squared x equals, I don't know, 1/2 sine x, right? When you look at this problem, you go and say, oh, pi over 3. I'm sorry, pi over 6. Because pi over 6 is going to give you a half, so you have half times half. It's the same problem. It has to be solved the same way. You cannot cancel sine, because sine could also be 0, and you are not allowed to divide by 0. So it's the same way to solve this equation by subtracting 1/2 sine x. And then now when you factor out sine x, and you have sine x minus 1/2 equals 0. Here is the sine x equals 0, and this x is 0, pi, and 2 pi. Look how many, 3 solutions. You would lose them all if you just canceled sign on both sides. Do you see that? And the solutions that you would be able to get are sine x equals 1/2, which would produce x equals pi over 6, and 5 pi over 6 because the sign is positive in the first two quadrants. So you would produce 2 out of 5 solutions on 0 to 2 pi if you cancel the sign on both sides. So this is one of those things where we have to be very careful in mathematics and just can't cancel willy-nilly. Right? You have to go and say, if I must divide by x because that's the only way to proceed, then let me on the side do a problem which forces x to be 0. Because as soon as in a problem is you divide by x, it immediately assumes that x cannot be 0, and you see that the lost solutions immediately appear if you ignore that fact. So that's just general rule of solving equations. And now for those linear systems, you're hoping for symmetries, which reduces calculation. If you don't have symmetries, the only advice that I need to repeat is always keep all of your equations on a pile, copying even the equations that you didn't use in a previous step, or maybe even previous 2 steps. Being lazy and careless while solving these problems will just make the matters worse. It will just make it worse, because you will have to scroll and go and look for the extra equations, and it's so easy to get lost if you have a lot of stuff that is written down. So keep it organized, and you should not have many issues. You might be running in circles a little bit and try this and try that. Obviously, with experience, it will get better, but just the basic skill is always keep the systems on a pile, and you can disregard every writing you had before that, because the system that you're looking at could be a starting point of any problem. That's it. Homework is open. Quizzes are going. Have tons of fun. And I'll see you tomorrow. Someone's lunch is ready.